Hello everybody, this is Cameron Snow with Danomics.com. In this video, we're going to be bringing you another Danomics Basics series here. And in this one, we're going to be having a kind of a double lesson here. We're going to be talking about both mineral inversion and porosity. And the reason why is these two really go hand in hand. So it's important to understand the interplay between the two, and maybe when you want to go with one method versus another. So by this point in your interpretation, you should have already gone through, got your log data cleaned up, done your clay volume interpretation, and if you're working with organic shales, you should have already done your TOC analysis. So with that said, now we're going to move on to the mineral inversion. And so we're going to select our inversion module here. And what mineral inversion does is it's often viewed as very much a black box by people, but it's really just a mathematical concept where you're doing a little bit of matrix algebra here. So what we're going to do is we're going to first of all take a look at some of the results, and then we're going to discuss the theory, and then we're going to talk about how that applies to calculating your porosity, and we'll talk about some of when you want to apply it and when you don't. So first of all, when we just pull up a very generic mineral inversion, and this is the case in Danomics or any other software, you have a default mineral model where you have things that you're using such as, quartz, calcite, dolomite, pyrite, your clay minerals, kerogen, water, oil, or gas. And what the model will try to do is it'll try to solve for the volumes of each of those minerals. And it will then give you some type of printout here. And in most softwares, what it'll do is it will give you some actual versus predicted curves in some type of display like this where you try to QC one versus another. Now, what is it actually doing behind the scenes to generate these results? Well, what it's doing is doing some matrix mathematics, some matrix algebra, and what we're doing can very well be displayed kind of here in this view. So what we do is we have the mineral properties for each of the minerals. So in this case, for quartz, we have its density response, its neutron response. It's in this case, we're using U as opposed to PE, sonic, and then we have a few other curves here, and we see that it corresponds to these curves here. And what we're showing here is that if you take this matrix of minerals, you multiply it by your mineral model, it will result in these curves. Well, we know the mineralogy in general. We generally know what mineral components are there. We know the curve data. So what we're doing is we are inverting to solve for the mineralogy. And that's how we get our mineral volumes. And that's also how we make the predicted curves, because then we take our known mineral properties, we multiply them by the mineral volumes that we have, and that allows us to generate the predicted curves. And when you think about it that way, it really tries to take this out of being a black box algorithm and into something that you can understand. You could actually do this, let's say, with something like the density for just a simple bimodal model. So if you think about, if you had a pure mixture between like a quartz and a clay, so you had a sandstone that's just half quartz and half clay, for example, and you know the density of quartz and you know the density of your clay, you could say what the density of the log should read in that case. And so all we're doing is we're adding more curves and we're adding more minerals. So a few notes on how do we decide what curves and what minerals that we would like to use. So in general, we're going to use our standard quad combo curves here. So density, neutron, some version of the PE. Some people like to use PE itself. Others like to use what we call the U value, which is just PE multiplied by density. You can use sonic. Sometimes you'll use conductivity. This can be debatable here. Conductivity, of course, has a non-linear response, so you have to use a slightly different approach when solving for that. We also have our clay volume that we can use as an input, our kerogen volume that we can use as an input, and we can use unity. And I'll explain what unity means here in a minute. First, I want to talk about using our clay volume and our kerogen. So we've already gone through and we've calculated a deterministic clay volume. So we can actually take that deterministic clay volume and plug it in to our mineral inversion. And this gives us an extra constraint. And this is because we think that we can actually get a really good estimate of clay volume using that deterministic methodology. The same is true for kerogen. We calculated our TOC. We then convert the TOC, which is in weight percent normally, to a volume of kerogen. And we did this in the previous basics video. And now we're putting that deterministic V kerogen back into our inversion to add another constraint on our inversion here. And then finally we have unity, and unity is just the fact that we know our minerals have to add up to 1. We have a whole rock, so the volume of our rock needs to sum up to 1. So if we have 50% quartz and 40% clay and 10% water, that sums up to 1. So unity is just that constraint there. Now, when it comes to setting up your mineral model, I like to say that we want to use a kind of a minimum viable mineral model here. So this means we want to have as few components as possible. Why is that? Well, when we're doing this inversion, it's actually a non-unique solution. So if you have, let's say, 1 curve and 2 minerals, you could mix that in certain proportions and come out with unity as a constraint and come out with a fairly exact answer. Now what happens if you put 3 minerals in there? Well, with 3 minerals, all of a sudden you go from having an exact answer to having an inexact answer. And that's because we are what we call being underdetermined mathematically. Now, the Danomics software will allow you to solve whether or not you are underdetermined, determined, or overdetermined. We have that functionality in there. But it really helps, especially if the minerals themselves are important to you, to be as close to determined as possible. So let's think about this with the context of what we are looking at here in the Powder River Basin. So for most of these formations, we do not have kerogen, we do not have pyrite, and we do not have dolomite. We have a fairly simple mineral model of quartz, calcite, clay, water, and in this case, oil. Now, when does it vary from this? It varies from this in formations such as the Niobrara, which is an organic shell, where we most certainly have kerogen and pyrite. So we'd want to enhance our mineral model a bit there. And that's also the case in the Mowry, where we know we have both kerogen and pyrite. If you have other zones, such as an anhydrite zone or a salt zone, you would want to go in and add those minerals to your mineral model in that case. Okay, so now that we've done this, and we can see that we've updated our mineralogy here. In most zones, it's just quartz, calcite, and kerogen plus the fluids. And in the Niobrara and in the Mowry, we have some kerogen and we have some pyrite. Okay, so once we have that, we need to QC our model. Now, how do we do this? The way we QC our model is we look at our actual curves and we look at the predicted curves. Remember, these predicted curves are coming from the mineral properties times our mineral volumes to get the predicted curve. And we want the predicted curve to be as close as possible to the actual curve. Now, we can look at some of these and we can see where we have big misfits. We have big misfit in our conductivity here, and that's because we're not using it as a constraint at present. We have big misfit in our sonic value, and we have a little bit of a misfit in our neutron. So when you're doing inversion, you need to ask yourself, where do I have a little bit of wiggle room in my interpretation? And the answer most of the time is in your clays. Because clay, we often don't know the exact properties of. We're not solving for kaolinite or smectite or illite. We're solving for a generic clay. And what I like to do is I like to make cross plots here. So we can make a cross plot of, let's say, our sonic versus clay. So this is a DT clay cross plot. And we can look at this and we can see that our DT is increasing as we move to higher values. But we see that in general, even if we extended this trend out to a value of 1, and we could even come in here if we want to and add a regression, so we could add a linear regression to see where this would extrapolate out to as a value of 1, and we can see that it's under 100 here, and we can see that in most cases, even at our higher clay values, we're only at value of around 80, and we extrapolate this out. So let's set this value at about 90, and now we can always come in and update this. Okay, so we can come in and do that. And when we do that, we now see we get a much nicer match between our predicted and our actual sonic values. Now we could do the same thing here. Let's make a custom cross plot. And in this case, we'd want to, on our x-axis, we would have our V clay. And on our y-axis, we might want to have our PE curve. So let's put PE on here. And we can see we don't have anywhere near as good of a trend here. But what we do see is that, the highest our PE ever really goes, especially out here on the high clay end, is around 4. And remember, this is a density. Our U property is density times PE. So if we take about a 2.75, multiply that by 4, we get a value of around 11. So we'll put 11 in here for this. And this will change our mineralogy a little bit, but we already had a really good fit between PE and our property here. And finally, the last thing that we can change is our neutron. So if we look at our good old neutron density cross plot, and we're going to turn that regression line off just to clean this up a little bit, we can see we put it out here to a value of around 0.45. That may be a bit high, but we can certainly experiment a bit with that, and that tightens up our fit with the neutron curve a little bit there. And so now we see we're getting an excellent fit with respect to our clay volume, our kerogens, and all these curves. Now the one curve that we don't have a great fit on right now is our conductivity. Now a lot of people don't like using conductivity. What I like to do is I like to get everything else set, and then if I need to, I'll put in my conductivity. And in this case, we'll put that as a fit, so we're solving for it. And we see that we now get a really good fit in our inorganic shells, but where we're still getting kind of a poor fit here in the organic shells. So if we look specifically, like let's say at the Maori Formation, and that's because there's excess conductivity due to the presence of hydrocarbons in our section. So it's an organic shell, it's generating hydrocarbons. We often have excess resistivity in these cases because it's an organic shell instead of an inorganic shell. And so there we go. We now have our mineral model done, and we can see exactly what we're predicting here. So now we've got our mineral volumes, and we can use those in a number of different ways further downstream. But what I really want to focus on is our grain density here. So the main output, in my opinion, of the mineral inversion is our grain density. So the grain density, this is a product of the mineralogy of the frame minerals or the grain. So we're not looking at the fluids here, just the minerals. And we can see that in a lot of cases, our grain density is actually higher than what we would maybe consider putting it for a quartz sandstone. So we would actually be underestimating our porosity if we put in a value of 2.65 into a density porosity equation. We should be using something closer to 2.7, and that's because we have some calcite cements. It's also because we have some clay minerals in here. And this is really important if you are working in some of these high clay sandstones or more shaly sands, it can really make a difference. And how would you tune this? Well, what you would do is you would take your core or your cuttings and you would take it to the lab. You would have grain density measured as a property. It's a really robust and easy to measure property. It can be done with the routine core analysis, and that's how we would QC that. Is we would QC the grain density that we're predicting versus the observed grain density. Now, once we have our inversion, we have this grain density. There are a couple of different ways that we can use it to calculate our porosity. Now, when it comes to calculating porosity, there are a number of different methods that are available to you. You could do a neutron density porosity, a density porosity, a sonic porosity. You can use the exact sum of the fluids that comes out of the mineral inversion porosity, which we call the strict option here, or you could take the grain density out of the mineral inversion porosity and then use your own fluid density. So you have a number of options here, and let's talk about some of these, and let's see how changing our option here changes things. So with a neutron density porosity, I often feel like we are overestimating our total porosity, especially if we are in a shaly sand system. When we look at the density porosity, the main thing we need to set here is our Roby clean 1 parameter. So, we need to set that, and we want to use a value of about 2.65 for quartz sandstone. And remember, we're mainly talking about total porosity now. We'll get to effective in a minute. With your sonic porosity, you'd need to go through and calibrate this. Typically what you'd like to do is go through and calculate both the density porosity and the sonic porosity and get a match between those, and then you can feel comfortable using either one. Now, since we've done the mineral inversion, I like using the mineral inversion porosity. And because I think that gives us the most robust answer across our area. So that's the one that we're going to go with here. Now, when would I opt for a density porosity over the mineral inversion porosity? If I don't have a lot of other data. So if I don't have my neutron, I don't have a PE, I don't have a sonic, well then your mineral inversion is not going to give you a good answer. In that case, it's better to use a deterministic density porosity, in my opinion. However, if you do have the additional curves that allow you to do that mineral inversion, I think the inversion is the way to go. Now, the last thing I want to talk about here is total to effective porosity. So when we measure stuff in the lab, we are measuring a total porosity. Now, a lot of people, just due to history, like to talk about an effective porosity. And what that means is you have to estimate a clay porosity. So you can strip out the fraction of the porosity that is associated with the clays. Now this is something that we cannot measure. There is no measurement that allows you to go from total to effective. So it's a bit of aesthetics. It's a bit of convention in here. And I want you to do a little thought experiment. If you have a very clean sand, so if you're working in the Gulf of Mexico and you have a sand that has less than 5 or 10% clay by volume, well, your clay porosity is hardly making any difference at all. Your effective and your total are essentially the same. If you're working in an organic shale, much higher volumes, you're going to have a hard time making any type of conventional measurement of porosity. We have to go to our special core analysis there. You're having to do things like crush rock methodologies. So in that case, we're dealing more with total porosities anyway, and we don't need to worry about the effective. So I personally, tend to look at total porosities, and if I want to discriminate between clay rich and clean intervals, I'll just use my clay volume to make that separation. So, it can be a bit controversial, but I think a lot of petrophysicists have really migrated to using a total porosity when they're doing their calculations, when they're applying discriminators to things like net reservoir and net pay, as opposed to using an effective porosity. Because once again, if you're dealing with clean sands, they're almost the same. If you're dealing with shaly sand systems like what we see here in the lower Parkman, or what you would see in an organic shale, where you maybe high clay anyway, you don't want to use your conversion from total to effective as a discriminator. You want to use clay volume as the discriminator anyway to determine the difference between reservoir and non-reservoir rock. So that is it for this lesson. I hope this video was useful to you. We'll continue with this Danomics Basics series, where we're going into a little bit of light education here. If you'd like to learn more, you can always contact me at sales@danomics.com. Thank you.